Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 5.2, Binomial Probability Distributions. So in this lecture, we're going to examine binomial probability distributions. We'll look at its characteristics, different notations that is associated with binomial distributions. We'll look at using probability distribution tables to calculate probabilities, as well as how to use StatCrunch to get those values. We'll look at some characteristic equations for the binomial probability distribution, and then we'll use those characteristic equations to determine usual and unusual distribution values. So now at this point, we're going to be describing particular probability distributions. From the last lecture, we described probability distributions in general, and now we're going to get into describing specific types of probability distributions, starting with the binomial probability distribution. So the lecture for this section presents a basic definition of a binomial distribution, along with notation and methods for finding probability values. Binomial probability distributions essentially are for circumstances in which outcomes are either this or that. So for example, you have items that are defective or they're acceptable. You have people who survive and people who die. So when you have only two outcomes from a procedure, typically a binomial probability distribution will be an excellent way to characterize that data set. We're also going to look at important characteristics of the binomial distribution, measures of center, variations of value, spread of values across a distribution, because these, again, are values that we use to describe a data set. And so the data set that's creating our distribution, we're going to use these same values to describe that distribution. So we're also going to learn how to interpret and understand those values. So let's get started. First, let's look at some characteristics for the binomial probability distribution. A binomial probability distribution results from a procedure that meets all the following requirements. So just as we saw for a distribution that can be called a probability distribution, there are certain requirements that must be met. We have the same sort of scenario with particular types of distributions, and the binomial probability distribution is no exception. So the first requirement that we have is that the procedure has a fixed number of trials. Second, those trials must be independent. That means the outcome of any one trial is not determined or influenced by the outcome of any of the other trials. So all the probabilities that are associated with each number of trials is independent. Third, each trial must have all outcomes classified into one of two categories. So we commonly call these categories success and failure. Success we can define any way we want, but the way we define success will determine many of the characteristics of our distribution. But we can define it any way we want. And fourth, the probability of a success remains the same in all trials. Again, the trials are independent, so it makes sense that the probability of success would need to be the same for all of the trials. If any one of these requirements are not met, then the probability distribution you're looking at is not binomial. It's something else. So you'll have to find some other distribution to fit your data to. Let's take a look at an example. And you got to know it. I'm back with the waffle cones. So if you have your ice cream, you'll feel free to pause the video, go get you some, then come back and start the video. Otherwise, I'm sorry, but you're just going to have to suffer through. So, could you model the following situation with the binomial probability distribution? So we're surveying 150 random adults about their favorite ice cream flavor. Could we model this situation with the binomial probability distribution? Well, let's take a look at each of the four requirements to see if we meet all four. First, the probability needs to have a fixed number of trials. And in this case, yes, we do have a fixed number of trials. There's 150 subjects that we're surveying. So this 150 adults represents a fixed number of trials. Second, the trials must be independent. Are these trials independent? Well, yeah, each trial is independent because asking someone about their favorite flavor of ice cream, and their favorite is their favorite. It's not determined. Well, you would think it would not be determined by what other people answer. Hopefully, we're not, asking people while they're in groups, because that would potentially bias our data set. Because you might have some people who say, yeah, well, my flavor is really vanilla, but because I don't want to look like a square, I'm going to say chocolate like everybody else. But generally speaking, yeah, the trials are going to be independent, so we'll say we have that requirement met. Each trial must have one of only two outcomes. Well, how many outcomes do we have when we survey each adult about their favorite flavor of ice cream? Well, there are many, many possible outcomes. I mean, this is ice cream we're talking about here. Thank goodness there are more than just two possible outcomes for a favorite flavor. There's many, many different varieties. And that's why I scream, you scream, we all scream for ice cream, because there are many different delicious possibilities that we could have for ice cream flavors. So each trial can have more than just, one of two outcomes. Fourth, the probability of success remains the same in all trials. And yeah, we're going to say this is going to remain constant, regardless of how we choose to define our success. So we see that we meet 3 of the 4, but in order to be a probability distribution that fits the binomial probability distribution, we have to have all 4 met. So because we missed 1, we would say no, modeling with the binomial probability distribution is not appropriate. Let's look at another example, again involving waffle cones. How about surveying 150 random adults about whether they like dipped waffle cones? Okay, so let's look at this one. Compare with each of the requirements for a binomial probability distribution. First, the procedure has a fixed number of trials. Yes, we have a fixed number of trials. There are 150 subjects, so the number of trials is fixed. 2, the trials must be independent. And yes, we're going to say that each trial here is independent. 3, each trial must have one of only 2 outcomes. Do we have this requirement met? The answer is yes, we do have this requirement met. Either you like dipped waffle cones or you don't. Okay? There's no fence setting when it comes to dipped waffle cones. You either like them or you don't. So there's only 2 possible outcomes, and you're going to get one of the 2 when you ask the question. So that requirement is met. And 4, the probability of a success remains the same in all trials. And we're going to say yes, that it does remain constant regardless of how you choose to define success. So therefore, we have all 4 of our requirements met, and that means yes, modeling with the binomial probability distribution is appropriate. Let's look at another case, and this time I'm going to give you opportunity to answer each of the questions associated with each of the requirements so that you can learn a little bit more about getting this process integrated into you. So, we're asked to evaluate 3 marbles are drawn from a bag without replacement, and the green ones are noted. Could we model this situation with the binomial probability distribution? Well, let's look at our requirements. The first requirement is the procedure has a fixed number of trials. Do we have this requirement met? Yes, we do have this requirement met. We're drawing 3 marbles from a bag, so that's a fixed number of trials. 2, the trials must be independent. Are the trials in this case independent? No, they're not independent because we're not replacing them back in the bag. Okay, we're drawing from the bag without replacement. That means the trials are dependent, not independent, because the probability of getting a certain color marble with each draw that we take from the bag is going to be different because we're not putting the marbles back in. So our trials are dependent. 3, each trial must have one of only 2 outcomes. Is that the situation here? And, well, not necessarily. There's as many outcomes as there are color marbles in the bag. If we have only 2 colors of marbles in the bag, then, yeah, you're going to get one or the other with each marble that you draw out. But we don't know that. All we know is that there's one color that's in the bag. We presume there's at least one more, but there may be others in addition. So we're going to have to say, no, each trial has as many different outcomes as there are colors in the bag. We're going to say that requirement's not met. 4, the probability of a success remains the same in all trials. Here we see the probability of success changes with each marble drawn because, again, they're taken without replacement from the bag. So now we see that we have only one of the 4 requirements that are met. So therefore, we conclude that no, modeling with the binomial probability distribution is not appropriate. We need to find a different distribution to model our data. Let's look at another case involving experimental drugs. So suppose we give experimental drugs to 85 patients to find the number of favorable responses. Could we model this situation with the binomial probability distribution? I'll give you a moment to figure this out. And then we'll go through how to get our correct response step by step. Okay, so let's take a look at each of the requirements for the binomial probability distribution and determine if we have those satisfied. So what's the first requirement for the binomial probability distribution? Well, I hope you said fixed number of trials. That's the first requirement. The procedure has a fixed number of trials. So now that we know that that's a requirement, let's look to see if we have it met. We find that yes, there are 85 subjects, so the number of trials is fixed. What's the second requirement for the binomial probability distribution? The trials must be independent from each other. Well, is that what we have in this instance? Are the number of trials independent? Yes, each trial is independent. Whether or not one patient responds favorably or not to a particular drug is not going to be determined by the response of any of the other patients. So each trial is independent. What's the third requirement for the binomial probability distribution? I hope you said that each trial must have one of only 2 outcomes. So, is that the case here? Does each trial have only one of 2 outcomes? Yes, in this instance we see that each trial has only 2 possible outcomes and you're going to get one of them. Either the drug works and provides a favorable response or it doesn't. It's one or the other. Again, there's no fence sitting here. What's the last requirement for the binomial probability distribution? Yes, the probability of a success remains the same in all the trials. Do we have the same probability of success for each of the different 85 trials that we're testing? Well, yes, essentially we do. Remains constant for each of the patients, so therefore we have that requirement met. So, is the is the binomial probability distribution appropriate for modeling this data set? The answer is yes. Modeling with the binomial probability distribution is appropriate because we have each of the 4 requirements met. Let's take a look at some of the notation that we use when talking about binomial distributions. First, we're going to use a lowercase letter n to denote the number of fixed trials. This means that n is always a whole number. You're not going to see any decimals or fractions here. It's always a whole number. It's the number of fixed trials. We're going to use a lowercase letter x to denote a specific number of successes in n trials. So x is also going to be a whole number. It will be no less than 0, because you can't have a negative number of successful trials. But it's not going to be any greater than n, because you can't have any more successful trials than you have actual trials. So it's going to be some number. It's a whole number between 0 and n. This is our random variable. We're going to use the letters S and F to denote success and failure. And again, we can define success any way we like. Then we're going to use, and this is the part that kind of throws me, because the capital letters S and F are used to denote success and failure, but then the lowercase letters P and Q are used to denote the probabilities of success and failure, respectively, in any one of n trials. So, typically, in a problem statement, you know what the probability of success is, based on how you define success. Well, then you also know what the probability of failure is, because think about it. Something is either a success or a failure. It's going to be categorized as one or the other, and therefore, success and failure are complements of each other. So if you know what the value of one is, just subtract it from one, and that gives you the value for the other. Because the only way you can get, success and failure, it's like that comprises the entirety of your possibilities there. So you're going to add them together to get one. And so the probability of x is the probability of getting exactly n successes among n trials. And the way we calculate that is with this handy-dandy equation here. Now, before you start freaking out, yes, you can use this equation if you want to go purely old school. But, of course, we're not going to go purely old school for most, if not all, of our problems. Okay? There are ways to calculate probabilities for binomial distribution in StatCrunch. Other software programs have similar capabilities, functionality. So you're gonna be thankful that you live in the 21st century. But just to make you a little bit more grateful you live in the 21st century, let's consider an example in which we look at each of the different parts for the binomial distribution so we understand where the numbers are coming from. So the probability of a certain number of successes in n trials has 3 parts to it that we're multiplying together. The first part is the number of outcomes with exactly x successes among n trials. This part of the probability equation for a binomial distribution, probability distribution, should look familiar. Do you remember when we were looking before at combinations? If you do, then this should look very familiar to you because it is the actual form of the equation that we use to calculate the number of possible outcomes when the order of the range of the items in the sequence did not matter. And that's what we have here. So the number of outcomes of exactly x successes among n trials. We don't care about the order of the successes. We just care that there's a certain number of successes when we have a certain number of attempts. So that's the first part of our equation, the total number of outcomes. Then we're going to multiply that by the probability of getting x successes among n trials. So we just take the probability of success and we multiply it by the number of times that we're looking for the number of successes. That's the second part. Then the third part is going to be the probability of failures among the n trials. So remember, the lowercase letter p represents the probability of success. X is going to be that whole number, the number of successes that we want. And then Q is going to be the probability of failure. So that's the complement to the probability of success. So we just subtract the probability of success from 1 to get that net value. And then the exponent for that, n minus x, well, there's only n trials total. So we're going to do a sort of a complement calculation there as well. So total number of trials is n. If x of them are successful, then n minus x will be the number that are failed. This then comprises the parts for our distribution for calculating probabilities according to the binomial distribution. As I said before, let's run through an example problem to show you how this is done purely old school, so that in the very least you are grateful for living in the 21st century. Now, some of the steps of this old school method you're still going to have to do when you use StatCrunch or any other type of statistical software. Those portions are going to be at the forefront. So let's look at this example and show you how this is done. Suppose a survey reports an 85% chance that a randomly selected adult knows what Twitter is. What is the probability that exactly 3 of 5 randomly selected adults know what Twitter is? The first thing you want to do when approaching these problems is define what success is. What does success mean? So in this case, let's say success means knowing what Twitter is. Okay? Now we've defined success. The next step is to define what our variables are. So when we look back at the problem statement, here's what we get for our variables. N is the total number of trials. So we're randomly selecting 5 people and then getting the probability of 3 of those 5. So 5 is going to be the total number of trials, N. 3 is going to be the number of successes. This is our random variable. We want the probability of 3 from our distribution when the total number that we could ask would be 5. Now, the probability of success, P, is going to be 85%. That's because we define success by knowing what Twitter is, and the probability that someone knows what Twitter is from our problem statement is 85%. So this is the probability of success. The probability of failure, Q, is then the complement of the probability of success, P. So we take 1 minus 0.85, and that gives us 0.15 for Q. Now we know what our variables are, we can go ahead and calculate out our probability. Here's that purely old school equation, so we just substitute the values in for what we know. So everywhere we see an N, we're going to put a 5. Everywhere we see an X, we're going to put a 3. Everywhere we see a P, we're going to put 0.85. And everywhere we see Q, we're going to put 0.15. Punch this out on our calculator, and out comes 0.138. So there's a 13.8% probability, or almost a 14% chance, that exactly 3 of 5 randomly selected adults know what Twitter is. Of course, as I said before, most of what we do when we're calculating these probabilities is not going to be using the old school method. Because, just look at this. This is messy. This is complicated. Well, it's not really that complicated. If you know what the formula is, and you actually do have this formula for your probability on the insert to your textbook. So you don't need to memorize anything. So, all things being considered, if you wanted to go back and do the old school calculation, you could do that. However, there are easier methods for calculating the probability. One of them is to use what's called a binomial probability distribution table. So we have this equation that's been calculated out for many different possible variations of total number of trials, number of successes, and different probabilities of successes. And they've been put into tabular form, so we don't have to punch the numbers out. from a calculator every time we want to calculate a probability with the binomial distribution. Now, this is not purely old school, but it is an old school method of calculation. I remember when I was in college, this is the way that we actually solved probability problems with different distributions. You'd find a table for that distribution, and then you would use it to calculate your probability. Nowadays, here in the 21st century, we actually have software that does all of this for us. So the software is, of course, the easiest method, and in a moment, we'll get into using StatCrunch for solving this. I want to go over how to use the distribution table, though, because there are some problems in your assignment that require you to use the table. Again, I'm listing require in what would you call air quotes, okay? Because if you really wanted to use StatCrunch to solve those problems, you could. But let me show you how the table is supposed to be used so that if you want to use the table, you can do that. Here we have a problem where we're saying, assume that a procedure yields a binomial distribution with 5 trials and 45% probability of success. Use a binomial probability table to find the probability that the number of successes is exactly 3. So, similar to what we were looking at before, only this time the probability of success is 45%. Let's learn how to use the distribution table to solve this problem. So the first thing we want to do is find the section in our table that corresponds with the number of trials. So, how many trials do we have in this particular problem statement? Well, I hope you said 5, because that's what we see here in the problem statement. We have 5 trials. So now we're going to go to our table, and out there on the far left, in the column labeled N, we're going to look for the number 5. And we see that number here. So that means that this portion of the table is going to be our area of interest. Now what we need to do is find the row of interest and the column of interest. So first let's look for the row of interest. The way we do that is by finding the row for the number of successes in our particular problem. So how many successes are we asked to find the probability for? I hope you said exactly 3, because that's what we're looking at here in the problem statement. So we want to go and look in that next column to the right of the 5, look for the 3. And that row for the 3 is going to be our row of interest. Now we need to find the column of interest. So the column of interest is headed with our probability of success. What is the probability of success from our problem statement? Again, 45% is our probability of success. So we're going to go to the top of the table and find the column that's labeled with 45%. That's this column right here. So now we have our column of interest and our row of interest. We're going to look for the point where those two intersect. So the value within that intersection point is our value of interest. In that case, this is 0.276. That then is the probability of getting exactly 3 successes among 5 trials with a 45% probability of success. This is our answer, 0.276. Of course, as I said before, doing this in StatCrunch is much, much easier. So once you don't even have to have data in StatCrunch. You can just go strictly to Stat, Calculators, then Binomial. You'll get this nice little window that pops up in your results window, and then you just enter the parameters and press Compute. So here's our window that pops up. We're going to enter in our parameters. So notice we have n equals 5 down at the bottom. Then our probability of success is 45%. We want the probability of exactly 3 successes. So that means from our drop-down menu, we're going to select the equal sign because we want exactly 3. And then we're going to put a 3 next to it. And then we hit Compute. And notice how we get the same number that pops out at the end. So 0.276 is the probability of success. Now, if you're asked to solve with a distribution table, you can go to StatCrunch and put the values in, because these three values you're putting in to your StatCrunch results window, those are the same numbers you use to use the distribution table with. So you could totally skip the table if you wanted to and just use StatCrunch. I think there's some value in actually learning how to use the table. If nothing more, it gives you an appreciation for living in the 21st century and having software that calculates everything for you. But hey, if you want to just go ahead and use StatCrunch for everything, yeah, there's nothing really stopping you from doing that. Let's look for some examples of characteristic equations for binomial probability distributions. These are equations that describe characteristics that we then use to describe the binomial probability distribution for our data set. Now, we have some variables that are basic to binomial distributions. N is the number of fixed trials, P is the probability of success in one of the N trials, and Q is the probability of failure in one of those N trials. So the first characteristic equation we're going to look at is for the mean. This equation is simply the number of fixed trials times the probability of success. So N times P, that's your mean value. Really simple calculation. Variance is calculated by taking the number of fixed trials times the probability of success times the probability of failure. So looked at another way, you could say that this is simply the mean value multiplied by the probability of failure. The standard deviation, as always, is the square root of the variance. So we just take the square root of the product of the total number of trials, the probability of success, and the probability of failure. Or we could take the square root of the mean times the probability of failure. These three equations are pretty basic for describing binomial probability distributions, and you'll need to know them to answer questions on your assignments. Let's look at an example to illustrate. In a clinical test, 34.2% of participants experienced unintended vomiting when given the standard dose of a certain drug. Kind of makes me wonder that unintended vomiting, so we're going to give this drug to people and they're going to intend to vomit it up. That's how awful this stuff is. And I don't know what they're giving them. I mean, maybe it is that awful. I don't know. It just seems kind of weird to talk about unintended vomiting. Anyway, be that as it may. If we have 8 subjects that are randomly selected and then treated with the standard dosage of this drug, what is the probability that at least 6 of them will experience vomiting? And again, it's the unintended vomiting here. Well, first of all, let's go into StatCrunch and put in our variables. So we've got 8 subjects that we put in. We've got the probability of success, 34.2, so that's 0.342. Remember when you're putting your probabilities in to put it in decimal form. If you put it in percent form, StatCrunch won't accept that. You're gonna get thrown back to the beginning. So just go ahead and make sure you put a decimal value in for your probability. And then we want that at least 6. So that means greater than or equal to 6. So we put that in, press compute, and out comes our probability, 0.022. This is the probability that at least 6 will experience vomiting. Note that this is actually the sum of all the individual probabilities from x equals 6 to x equals 8. If we were using the table to solve this, we would take the probabilities for x equals 6, 7, and 8 and add them together. So we have those probabilities listed there. We'd add them together, and that gives us the 0.0224, which is our probability of at least 6 successes. Notice we're defining success as vomiting. Sometimes the way that you define success sounds a little quirky, but the way you define success can make the problem easier to solve or harder to solve. So the more times you go through these problems like this, the easier it becomes to determine, okay, so I'm going to define success this way so that it becomes easier to solve the problem. What is the mean and the standard deviation? of this distribution? Well, we know how to calculate the mean. That's simply going to be taking the total number of trials, which is 8, multiplied by the probability of success, which we get from the problem statement, 0.342. That gives us 2.736. Standard deviation, we get the standard deviation by taking the mean value, multiplying by probability of failure, and we get the probability of failure as the complement of the probability of success. So 1 minus 0.342 gives us 0.658. Multiply that with the mean, take the square root, and out comes our standard deviation of 1.342. And that's really all there is to it. Let's look at an example involving a survey of window contractors. So a local window manufacturer named Sureglass commissioned a survey of randomly selected construction contractors in the area and found that 72% of them use their windows. So 72% of construction contractors, when it comes to installing windows, they're going local. Now, suppose we sample 6 contractors from the area. What is the probability that exactly 5 of them use Sureglass windows? Well, if we go into StatCrunch and go to our binomial calculator, we can put in the values for our variables. So we have 6 trials, that's n. Then with probability of success is 72%, so 0.72. And then we want the probability that 5 of them, exactly 5, so that's going to be equals 5. And then we press compute, and out comes our probability. If we blow that up so we can actually see it better, notice how we have the different variables and how it associates with the wording of the problem. So exactly 5 means we want to select equals from our drop-down menu and then put 5 in the field next to it. That gives us a probability of 0.325. What is the probability that at least 5 use Sureglass windows? So now it's not exactly 5. Now it's going to be at least 5. We don't need to go through the steps all over again. If we already have the window up in StatCrunch, all we have to do is go down to that drop-down menu and select the greater than or equal to sign, and then StatCrunch will automatically compute the new probability for us, 0.464. Notice that at least 5 translates into greater than or equal to 5. What is the probability that all 6 use Sureglass windows? Now, some students, when they see this problem, are tempted to select everything in the probability distribution. They're looking at that word all, and that's not how you would solve this problem. To solve this problem, all 6 means exactly 6. So we're going to change that our greater than or equal to sign to a full equal sign. We'll change that back, and then we'll just put 6 in for 5, press compute, and out comes 0.139. Is it unusual for 5 of 6 contractors to use Sureglass windows? Well, what do you think? To evaluate this, you're looking for the probability for 5 of 6 contractors using the windows. We calculated that at the start of looking at this slide, so that's going to be the 0.325, and 32.5% is greater than 5%. So no, it is not unusual for 5 of 6 contractors to be using these windows. We just used the 5% threshold approach to determine that 5 contractors using Sureglass windows is not unusual. Let's see if we get the same result using the range rule of thumb. First, we need to calculate the mean and the standard deviation. Notice that in this instance, when we're using StatCrunch, we don't get the mean and the standard deviation coming out of the actual distribution. And because we didn't have any actual data, we can't use the custom calculator option in StatCrunch to give us the mean standard deviation. So we're going to have to use the formulas. Fortunately, the formulas to calculate this by hand are really simple. First, let's do the mean. The mean is just the total number of trials times the probability of success. So we take 6, which is the number of trials. We randomly selected 6 people. And then the probability that they use the windows, the probability of success is 0.72. Multiply that out and we get 4.32. The standard deviation, we're then going to take that value and multiply it by the probability of failure and then take the square root. So the 4.32 times the probability of failure, which is the complement for the probability of success. So 1 minus 0.72 gives us the 0.28. Multiply that by the mean, take the square root, and out comes 1.1. Then we take 2 standard deviations from the mean on either side to find our min and max usual values. So the minimum value is going to be found by subtracting it. Wow, I don't even know why there's a plus sign there. That should be subtracting. And you see that there in the calculation. And that gives us the right number, 2.12. Then the maximum value is going to be found by adding instead of subtracting. And we get a maximum value of 6.52. So having 5 contractors is inside this range of usual values. So it is not unusual. We reach the same conclusion. Let's look at another example involving the recognition rate of the McDonald's brand. McDonald's brand has a 95% recognition rate. For a special focus group of 12 randomly selected adults, find the mean and the standard deviation. Okay, so first up, what we're going to do is look at the mean. So the mean value, remember, is the product of the total number of trials and the probability of success. We have 12 randomly selected adults and a 95% recognition rate. So we're going to multiply those two together, and that gives us 11.4. This is the mean value of our binomial distribution. Standard deviation, we're just going to take the number of trials times the probability of success times the probability of failure, and then take the square root. So notice that the probability of success is 95%, means that the probability of failure is 5%. Again, we just subtract from 1. They're complements of each other. Punch all this out, and we get 0.8 for our standard deviation. This is then the mean and the standard deviation. Suppose we wanted to know the range for the usual number of people who recognize the McDonald's brand. Well, we can use the range rule of thumb to get that. So our minimum value is going to be 2 standard deviations below the mean. So we take twice 0.8, subtract from 11.4, and that gives us a minimum value of 9.8. The maximum value is found by adding instead of subtracting. So we're going to take 11.4 and add in twice the standard deviation of 0.8, and that gives us 13.0. This then is the range of the usual number of people who recognize the McDonald's brand. So, having all 12 members of our group recognize McDonald's would not be considered unusual. However, having only 9 of the 12 recognize it would be. Likewise, it would be unusual for 14 members of our group to recognize McDonald's, since we're only asking 12 people. So getting anything more than 12 would definitely be unusual, and that's what this range maximum says here. 13 and above is considered to be unusual. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class and in the next video. Thanks for watching.